I briefly go over with you again some ideas for the quiz, and then we take the quiz, and then you go to lunch. Okay? With quantifiers and quantified statements, okay, it is super, super important that you go home and read the sections at night. Okay? It's gonna be easy, but yet it's gonna be difficult because it's so easy. Okay? It's so easy that it's hard. Okay? I don't know, but this is how it is. It blows my own mind. So, kind of to give you an outlook of the next week or two here, we're on Thursday, July 1st. Okay, if you guys look up here at the board, that's quantifiers and quantified statements. July 6th, Tuesday, when we come back, because we're not coming on Monday, right? Okay? You guys, I'm not coming. It's celebrating 4th of July.
Oh, okay.
Okay? So, can you guys, hey, listen, please. So, July 6th, we're going to do the same thing. We're going to keep going over quantifiers and quantified statements. July 7th, same thing. Next Thursday, you have your second exam, which will cover exercises 12 through like 19 or something like that. Okay? And then week 6, we start talking about sets. Okay? On week 6, I will not be here. It'll be on video, so I'll have videos that will be up on the board. You guys will watch those, okay? And they'll be in Canvas as well if you want to go back and watch them later. Okay, week 7, which is our last week, it's like exams and finals week. Okay? Tatum.
Can the videos be funny?
I don't know. I'm not that creative sometimes. I'm going to try to keep them shorter rather than longer, though. But I don't know if that'll work either. Yes? Email. I may or may not be able to answer. I'm going to be on a list today, so. Going to Bear Lake.
I have a question.
I love Bear Lake. Go Max and Thornton. Huh? We're on week 4. Okay, we're on the last day of week 4. Okay, other question? Yes? No, I don't go typically. I go with my family on the weekends and we go party. So, sorry. Questions? Okay, in Canvas, you'll see week 4, you've got one assignment this week, and that's exercises 15 and 16. Those should be done. Okay, if those aren't done, that's on you. We did most of them in class. Quiz 3, we'll do that today. Okay, go ahead and go to your notes. We're going to go over some more quantifiers and quantified statement ideas. We're going to start here again on the negation of quantified statements. We talked about it yesterday. We're going to talk about it again. Okay, real quick, we have 2 criteria that has to happen when we have a negation of a quantified statement. We have to make sure the truth value must be opposite the truth value of the original. And then the second one, this is the one we were confused on yesterday. So it's the form of a negation must hold for all terms and all predicates. So all terms and all predicates. If we look at our examples, we had example 1 and example 2 here in example 27 we had 1 and 2. Okay, we had all cats are tigers. The negation of all cats are tigers was some cats are not tigers. Okay, notice, okay, just a little, kind of to help our brains a little bit. The negation of a universal quantifier is what? The existential. So the universal has to change to existential, so it's got to be R or S. Right? Okay, then we have to make sure that all of the predicates are changing. So that the negation here from universal existential starts changing that idea. So you've got to go to the universal existential. That has to change no matter what. And then we have to have, well, if all cats are tigers, some cats are not tigers. So you can't just here you just put in some cats are tigers. Only the universal changed to existential. Here, only we can't just add a not and call it a negation. We've got to make sure that universal to existential changes or existential to universal. So the quantifier has to change as well, is what we're trying to get at. So the quantifier, and we have to either remove a not or input a not. Okay, so those two things have to happen. That's what helps meet criteria 2, so that we can meet criteria 1. So that'll fully change the truth value, okay, while meeting criteria 2 as well. Any questions on what has to change to get a negation of your quantified statements? The quantifier has to change, and we either have to add a not or take out a not, depending on what we're doing. So what we've got to do now is we've got to look at all this stuff symbolically. How do negations work symbolically? How do negations work symbolically? So what I'm going to have you guys do right now, go to example 12 in your notes. Example 12. So it's going to go back a couple weeks. Everyone should be flipping. Example 12. Follow the examples. You're on example. This is example 27. That means you got to go back 15 more, right? Page 20? Page 20. Okay? Page 20. Okay, the two things we're going to be using here to help get our negation symbolically are De Morgan's law and denying the antecedent. Okay, you guys see those on there? See, denying the consequent, sorry, not the antecedent, denying the consequent and the antecedent are both on that page. You guys see them? Yes? Okay, you see De Morgan's laws? So these rules, these facts, okay, they're going to come back into play right now for our symbolic representation. You guys need to be able to show a negation symbolically. So we can write it. We can go all tigers are cats. We know the negation is going to be some tigers are not cats. Right? We're saying here that W is the negation of P. They're logically equivalent. Which logically equivalent means what? They have the same what? Truth table. So, again, we're going to start with these statements. All tigers are cats. Some tigers are not cats. From our previous example, you guys stay on example 12, okay? So we're going to look up here while you guys are on example 12. You're going to help me out. W is logically equivalent to not P. The negation of P. So, let T be the predicate is a tiger, and C be the predicate is a cat. We've got to change, we've got to show how this negation works. So P can be written as, for every X, if X is a tiger, then X is a cat. You all good here on this symbol? I'm reading it. Right? Everyone good? So we've got to turn this symbolic statement into this, using our rules there on example 12. Okay, this is our P. Okay, we want to make P look like W so that, because we know W is logically equivalent to not P. So if we find how to make this, we find how to make the negation of P. Because they're the same thing. Huh?
I thought if you wanted to make a negation of a conditional statement on a biconditional statement, I thought you had to deny the consequence.
We're going to be looking at that, how it works. We're not quite there yet. Yes, you're on the right track. Okay, so we got to make our conditional statement into a conjunction essentially, and we got to change our universal quantifier to an existential quantifier. Okay, so that's what's got to happen symbolically. This is how it works. Again, you guys are on example 12, so you guys can see how this connects. So first, we say, well, we know there exists an x, where x is a tiger and x is not a cat, right? Is the same as w, which is the same as not p. So, which is the same as taking our p values. If we take the statement p, and we put a negation in front of this, we get this. Okay, so we took p and put a negation in front of it. Now we want to take this statement and continue to manipulate it. So here we can say, well, the negation's here. That means if I take the negation of our universal quantifier, and I take the negation of my conditional statement, I get this. Okay, this is by denying the consequent. Okay, denying the consequent. Grant, that's what you're getting at, yes?
Yes.
Okay? So now we go in deeper, we think about it. We can say, well, if we can say that for every x there exists, and there does not exist, I can't even say it, not an x for every, which is the same as not for dot, mean the same thing. So these guys mean the same thing. Okay, so they're logically equivalent, these ideas. Is everyone okay with that? Okay, so if I take something that's existing, it's logically equivalent to not for every and not for whatever's after it. So this is the dot, whatever's in that symbolically. Okay, then we get these statements from that. Okay, these are the other logical equivalences we can assume. Well, if we take the negation of there exists, that's logically equivalent to for every x, the negation of whatever it might be. So we can go from here to here. We can go this statement to this statement. We can go from here to here. So these guys are all logically equivalent. They're logically equivalent statements. Now let's think about this something. That's it. Let's do heads down real quick. Heads down. Let's try this. Look. Think about the 3 lines I have up here. Okay, think about the 3 lines I just showed you. I circled a pointed an arrow. Who's confused by those 3 lines that we just looked at? Who's confused? Hey, who's kind of confused? Hey, who thinks they understand what I'm talking about? Hands down, hands up. Good. So we're all kind of split. So to take an idea, okay, we're going to take this idea. We're going to do something over here on this board for just a second. They're not the same thing, but we're going to relate a principle, okay? So if I have an equal sign, that means same, yes?
Yep.
Logical equivalence means they have the same truth table, right? We're saying we can write this statement as this. Well, they're logically equivalent. This is the same as this. Kind of like, we can say 2a, which is 2 times a, right, is the same as 2 times a. Actually, let's do 4. 4a is the same as 4 times a. Is everyone okay with that? I can put a times sign here. That's the same thing, yes?
Yes.
Which is the same thing as saying 2 squared times a. 2 squared means 2 times 2, which is 4. Are these guys equal?
Yes.
They're the same. We wrote the same thing, they just look differently. This is the same as this. We can write them interchangeably. Yes, Greg.
So basically, the only thing we're doing is changing the quantifier and then negating the other thing, and negating the other thing.
Depending on where the negations are at, yes.
Okay,
Yes.
that makes much more sense.
So if you have a negation here, that's going to change the quantifier, which also negates the second statement. See how it negates here? So what we need to do is with this page, again, you guys are on example 12 still, I hope, okay? We're going to need that still. When you guys come back to this page, this is something you're gonna have to refer to, okay? This, just for your own notes, this is page 47. Again, don't go here right now. On page 47, you have these three logical equivalent statements that you're gonna have to know, okay? On your exam next week, at the end of next week. Today for the quiz, don't worry about this, that's fine. But for the exam next week, you need to understand how to do this. Yes?
So it's just the opposite truth value for each part of it.
Say it again.
So it's just the opposite truth value for each part of it.
So you're saying if they both negate here, they both don't negate here. Or they switch, the negation sign goes away, what you're saying.
Yeah.
Yes. But we're just trying to show you, this shows you how it works. I just need you to be able to say, well, this is the same as this. This is the same as this. This is the same as this. Okay, that's what, for us, if we can do that, we're on the right track. Okay? Yes?
So basically the universal is supposed to be the opposite truth value of the system.
It just depends on the situation. So I've got a universal quantifier here, that, and a negation here for the whatever statement's after that universal quantifier. That means that's the same thing as saying the negation of the existential and no negation here of the statement. So again, it depends on the situation on each one. Yes?
What's the point of having, like, switching those two?
We're gonna see. We're gonna see. So these rules, these ideas, combined with example 12 on your guys' notes, okay, we're gonna show how we can take a statement and write its negation, okay, or a quantified statement and write its negation. So you guys need to be able to, when your teacher says show their work in school, let's say you're supposed to solve for x. To show your work on an equation like this, you would say, okay, I'm going to distribute here, that's 2x plus 4. If you don't know how to do this, that's fine. Okay, you would subtract 4, that's 2x equals 8, and then you divide by 2, and x equals 4, right?
Yep.
Shows your work, right? Okay, what we want to do is take this kind of idea and say, well, with this quantified statement, show me how you get the negation. Show me the steps. Kind of like, show me the steps here, right? Show me how you get your answer. When we start with a quantified statement, and I say, hey, show me the steps on how you can get the negation, we're going to look at some examples on how you would do that. And you need these rules. Okay, you need these rules, and that's why we're covering them. I hope that leads into your question, okay? Yes?
What about the ones in
They're not as necessary, but yes. We don't want to ignore them, because they're all logically equivalent, right? This is logically equivalent to this, which is this. And same here. This is an important step, yes, but not as necessary as understanding that this gives you this, this gives you this, this gives you this. You do need to know this, yes, but we're getting a basic idea, I hope, so far. We'll see here in the example. Okay, do you guys stay on to example 12? So here's the thing. It says, knowing these relationships, you can use them to determine the negations of different quantified statements. We just talked about those relationships for a reason. That's why. Example 28 here. Let's look at this. Okay. Who can read this from where they're sitting? Go ahead and try it.
analysis, finding negation of P. Some books are novels, but E is the predicate, and the predicate is a novel. Symbolically, P is written as
There exists an X, where X is a book, X is a novel, right? Good. Yeah, it's hard to. This is still learning a new language. Don't. If you need help, let me know. Okay, that's good. Good job. Thank you. So we need to write the negation of P, right? This is P. That's P. The negation of P is saying, hey, look, take the negation. That's the negation of our whole quantified statement. Which, if you look up here, does it match up with 1, 2, or 3?
1.
Matches up with 1, right? So our end result should look like this. Yes? Okay, let's see how this works. So the negation of P is such that we put a negation sign in front of our whole quantified statement. That means our existential quantifier changes to a universal. And then we get a negation here. This guy right here, right? See how the negation sign goes right here in front of our conjunction? And then the negation of our conjunction, so this is using relationship 1 shown above. So guys, look, statement, reason, right? It's a proof. It's a proof. That's all it really is. Statements and reasons. When you do math like this, it's statements and reasons. You're just not writing out the reason necessarily. Okay? Give me 1 second, okay? So, next you say, well, this can happen because of this relationship here. And then you say, well, this conjunction, this isn't totally done. Okay? We've got to switch it up and say, well, that conjunction's got to change. By De Morgan's law, the negation of our conjunction is the same as saying the negation of our first statement as a disjunction with the negation of our second statement. That's De Morgan's law, example 12. Look at De Morgan's law in example 12. Do you guys see that? See that De Morgan's law applied here with conjunctions? You get a disjunction, the negation of two statements. Okay, Violet?
So when there's the negation sign outside the parentheses, does that mean it just makes does the negation of everything inside so it's the same as the disjunction?
Well, you have to, De Morgan's law says, look, if you're going to take the negation of a conjunction, that's the same as saying the negation of both statements as a disjunction. So yes, you're going to negate the first statement, bx, negate the second statement, nx, but you've got to switch from a conjunction to a disjunction. In a sense, if you're distributing that, you can't just throw it in there, right? You can't just negate both of these and call it good. When you negate both of these statements, it's got to be turned to a disjunction now by De Morgan's law. De Morgan's law says, hey, look, if this happens, that's equivalent.
So in the second row with the conjunction, why did they just put the negation sign in front of the ex and the nx?
Because this rule right here. Because we're going from this to this. The negation has to stay outside. So we can't combine a bunch of steps in one. We have to make it more simple. Okay? So we're going from here to here. That's because of relationship 1 up here. And now to be able to put that negation in like you want, you've got to say, well, I can do that because of De Morgan's law. So there's 2 things that have to happen to get to this point. Okay? And then De Morgan's law to the next part, well, if this is what I have a negation of 2 statements as a disjunction, and then I want to say, well, by denying the antecedent, again, look at example 12, by denying the antecedent, I want you guys to match this up, denying the antecedent. You get this, right? You get a conditional statement as if bx, then not nx, or not nx. Okay, so if x is a book, then x is not a novel. So this would be our negation of P, is logically equivalent to, for every x, if x is a book, then x is not a novel. Okay, therefore, not P is the statement, all books are not novels. Remember, this is just another way to write this. All books are not novels. Questions on example 28? What I need you guys to be able to do are these steps. Okay? That's where you guys have to get to. Okay, that's the end goal. Okay, Arena?
So
that says, hey, how do we get not P to look like this? So how do we get this statement here to look like this? It's just a how-to. Okay? Because we know symbolically, okay, we know when we're writing the negation of this, we know it's got to look like this guy here. We talked about it in previous examples. We're just saying, okay, how does it work logically? This is how it works by logical reasoning. Using all of our logic rules, that's how it works. Other questions? Yes, Grant? No. I'm just doing it. Okay, so, yes. On Tuesday, so what we'll do on Tuesday is we'll finish this negation idea. So we've got 3 examples we're going to go through. What I want you to do before Tuesday, you need to read through page 48 and 49. So write that down somewhere where you're going to remember it. Say, I need to read page 48 through 49. You don't have to understand it. I just need you to try to read it and try to understand it. Okay, page 48 to 49. Okay, your quiz, just to review real quick. Quick review, then we'll take the quiz and you guys will be out for lunch. You guys will get a question like this. We'll ask you to prove something. Okay, you have to write the symbolic form of your statements here. Okay, you have to write the symbolic form. You have to fill in a symbol here, symbol here, symbol here, symbol here. I gave you the statements. You have to give me reasons for the statements. So, using all of your examples in your notes, because it's over the note, right? It's a quiz. Using all your examples, you're going to have to go figure out, okay, which rule did we use? Did we use rule of bonus tollens? Did you use a conjunction? Did you use whatever it might be that you use to get the statement, which is already done for you, the statements are done. You give me the reasons on how they go from 1 to 2, 2 to 3, 3 to 4, 4 to 5. How do we get those statements? What logical reasoning can you come up with? This is the logical reasoning. Okay? You'll get a 2-column proof like that. Then you're going to have to fill in a truth table to show that our argument is valid. So, you have to show an argument is valid by using a 2-column proof. You have to show an argument is valid by using a truth table. Okay? Then, your last question on the quiz is very similar to number 17. Okay? You're going to have to identify predicate and term. You're going to have to identify the arguments symbolically. Okay, so the stuff we've been working with, you're going to have to write quantified statements symbolically. Okay? One quick thing so you have the answer. Exercise 17, we went over all the answers except for which number?
The last number 3.
Number 3. That might be beneficial to see number 3 at this point, right?
Yep.
Okay, let's see if you did it. Let's go ahead and I'll show you number 3 just so you have it. It might be beneficial to you. Okay? Here's exercise 17, number 3. No apples are bananas. No apples, so think about the word no, okay? We're looking at a universal quantifier when it says no. When it says not all, that's an existential. Don't let the word all confuse you. Okay? So no apples are bananas. That means for every x, if x is an apple, then x is not a banana. Right? Okay, you got to look at your words. Okay? Not all fish walk on land. Okay? There exists an x for where x is a fish and x is not not on land. Yes.
So how do you tell when to use conjunction, disjunction, and for arrows?
Existential, conjunction. Universal, condition. Yes.
Well, I did B differently. I don't know how to say it because I don't know how to say the words for it. How you do it.
This is what you would need. Okay, another idea, just real quick, while you're taking the quiz. If you look here on page 20 or 52, oh, this is not yours. This is the manual. So page, it's gonna be different for you. A good page for you to refer to is going to be page 41. Look at this. Okay, these are different ways to write universal statements. Okay, when you have a universal quantifier can make it so you can write it one of these 5 ways. An existential quantifier makes it so you can write it one of these 5 ways. You're seeing option 1 frequently right now. Today we talked about using option 1 for each one, but these also work. When you read it, I like to read it like this, with using the theirs, okay? It makes more sense in my little brain. So, when I read the universal quantifiers, I use 4. Yeah, it's just, again, it makes sense in my little brain. So, whatever works for you, use it. But those are the 5 different ways you can write universal and existential. Okay, so page 41. Open, no, open book, not open partner. So do not talk. Okay? If everyone stays nice and quiet, I've got a lot of candy to get rid of.
Oh, yeah.
Okay? The class yesterday couldn't handle it. Okay, so one person screws it up for the rest. Does that make sense? So you all get a piece of candy if you stay quiet till everyone's done. Deal? Okay? But again, one person can screw it up for the rest. I won't call out the person. If I notice it, it just won't happen. Does that make sense? Okay, just Violet.
Yeah.
So the rest of the class, got 20 minutes. Should be plenty of time. Yep, when you're done, be quiet. Raise your hand, flip it up.